Get started. So my son's here. He's the youngest member of the class. At some point, he probably will interrupt, but that's fine. We'll get as far as we can without that happening. Is there any questions from last class? Or about the logistics or anything that came to mind? Okay, so today we'll go through the second lecture. It's on something called evaluation frameworks. Evaluation frameworks is what the basis of your first assignment will be as well. So at the end of class, we'll go through the first assignment. And as we go through the class too, I'll try and make mention of the things that you'll look at or to pay attention to for your assignment as we go through. Okay, so last class we looked at STRIDE. Just to recap, STRIDE's a high-level methodology. What does that mean? It means that you could apply STRIDE to lots of different things. You could do STRIDE for hardware, you could do it for software, you could do it for procedures, human policies, whatever. So it's pretty versatile. The problem with it is you're not going to be able to do a deep dive probably with STRIDE alone. Okay? At best, it might help you brainstorm some ideas when you think about attacking the system. The other thing about STRIDE is STRIDE you apply to a single system. So I'm looking at this piece of software. I'm going to apply STRIDE to that piece of software. Okay? Attack trees, which we'll talk about next class, are similar, where you apply it to one thing. They're actually even more specific than you just apply to one system. You apply it to one security property you want to hold for that system. So you don't even look at all the security properties. You pick one security property of one system, and then you do an attack tree for it. And STRIDE, though, you can look at all the different properties that you would want from a single system. What we're going to do with evaluation frameworks is we're going to use it to compare multiple solutions. That's what it's good for. Okay? So you have different alternatives. You could do any of them. You have to choose. And so that's where an evaluation framework is going to help you. It's sort of based on this axiom, which is more from economics, but it applies, which is that normally if you have 5 alternatives for something, it's not the case that one is the best. There's one, it's the best alternative, and the other 4, no one would use. Usually if that were the case, then the other 4 wouldn't exist, or they wouldn't exist for very long. Okay, so whenever you're in a scenario where there actually are 5 different ways of doing it, and different people are using one of the 5, it means that there's probably some trade-offs involved, where this one might be better for security, but it's worse, it costs more, and this one's cheaper, but it's not as secure, or whatever the trade-off might be. Okay, and so evaluation frameworks are good for that as well, where there's different ways of doing things. There isn't a clear winner. Not everybody is going to agree that this is the best thing. And so what you do is you just present the alternatives. You try and assess what each one is good at and what each one is bad at. And you don't make a decision, okay? The evaluation framework just presents the information. Someone can look at it, and when I look at it, I might decide to go with solution A. You might decide to go for solution B because we have different preferences. The actual deliverable, like what does an evaluation framework look like? It's something you've seen before. You've seen it a million times in your life, maybe not specifically about security, but it's basically just a big chart. And the rows are the different systems that you're comparing, and the columns are like the properties that you want, and then there's some indication of whether this system achieves that property or not. Okay? So anyways, you'll see lots of examples of what they look like in a second. Actually, we'll go straight to it. So for example, let's say you're trying to choose between 3 cars. You've probably seen this kind of website. So there'll be a bunch of properties, and then you'll have a bunch of cars, and it will have all the different details of them, okay? Ours will be the same, except for our solutions will be will be rows as opposed to columns, right? Or there's other things comparing different lenders, different types of checkings accounts or whatever, okay? So this is an evaluation framework. It's the same deliverable. It's just a big chart that looks like that. And the reason it's hard to do is it's going to be hard really to come up with the columns and making sure they're sensible. coming up with, you can see in this middle one, it's a very simple thing. You either get the check mark or you don't, okay? And so for each security property, we have to think about what does it mean to get the check mark or not? Like where do we draw the line between whether something gets it or not? And so anyway, so it looks super easy. It's not like super difficult either, but it is more difficult than it seems, I would say. So it's sort of moderately difficult to do, yeah.
But I see that there could be also numbers and quantitative and qualitative adjectives that you can put on each one.
Yeah, exactly, yeah. So what do you actually put in each cell? Is the cell here you have a check mark or not a check mark? Some of them you have numbers, they represent prices. Sometimes it's more qualitative stuff. And so you can do your evaluation framework any way you want. Okay, so there is no rhyme or reason to do it. But the way we're going to do it in class, and there'll be slides on this in a second, but we're going to try and do the simplest possible. So the simplest possible will basically be either you get the check mark or you don't. So it's not the only way you can do it, but anyway, that's what we're going to strive for. And then because that's maybe not flexible enough, we'll have a sort of half category. So it's sort of like you either get the check mark, you kind of half get it, or you don't get it at all. And that type of framework, I've seen it in like hundreds of academic papers, and most security things you can whittle down to that. You're going to lose a lot of the detail and the nuance, obviously, but most things you can reduce to just one of three states. But yeah, if there's an absolute need to expand it to something else, you can do it too. There's no, all of this stuff like STRIDE and evaluation frameworks and attack trees, there's not like hard rules like you have to do it this way. It's sort of like you're doing it the way that's going to be useful for the person that's going to consume it, right? So that's the intent always.
So being readable is more.
Exactly. Yeah. So 100%. So that's the end goal. The end goal here is we want the thing that's the most readable, okay? So I'm going to give you a few tips. Like one is reducing to just check marks or not check marks. That will increase readability. And there'll be 2 or 3 other things that I'll suggest to you. And yeah, the end goal is always readability. Okay, other questions, comments? Okay. Yeah, and so this actually goes to that point is it's sort of, oh no, actually this is a slightly different point. An evaluation framework isn't going to make the decision for you. Okay, so just like this, it doesn't tell you what car to buy, right? If you're price sensitive, you might buy the middle car because it's cheaper, right? If you want the best mileage, right, then you might buy this car. I'm just sort of picking them, I don't know. If you don't know how to drive manual, then you want an automatic car, then you got to pick the first one or whatever, okay? So like people are going to have different preferences. An evaluation framework isn't making the decision for you. It's just showing you what the trade-offs are and you can decide. Okay, the final piece of an evaluation framework is it's meant to look more, even though it's about security, you're learning this in a security course. The end goal is not to just communicate security properties. The end goal is to communicate anything that the decision maker would want to know in making that decision, okay? So security is the obvious one, but another one is cost, right? If 2 systems cost different, right? Cost isn't a security feature, right? Something that costs more isn't necessarily more secure or less secure, but how much it costs is going to definitely be a factor that decides what I'm choosing, okay? But there's other things that are involved too. So it could be like, let's say it's some sort of software. Do I have to change all of your computers, right? Do I have to like maintain your computers? Like Concordia decides, oh, everyone now has to do 2-factor authentication, or everyone has to use a VPN in order to like log into this particular system, right? Well, now all of you need this VPN software on your computer. So all of those computers have to change. I have to put up a VPN server, right? So I have to change my infrastructure at Concordia in order to do it. You already have username passwords, but maybe it's an environment where you don't. Now I have to give out username passwords and people are going to forget their passwords and I need to reset them and things like that, right? So I add all this kind of extra infrastructure, okay? Another thing is usability, like can users actually use it, right? If users can't use it, then they're going to try not to use it. right? Instead of going through the VPN and doing it this way, I'm going to find some other way of doing it, or I'm not going to use Concordia services at all. I'm not going to use Concordia's email. I don't like it because I have to use a VPN, so I'll just use Gmail instead. Now, is that what Concordia wants? Do they want people not to use their own email? Probably not, right? And so sometimes you might drive users away based on the sort of the human factors that are involved, okay? So anyways, within evaluation frameworks, we're going to try and paint a complete picture, not just, the focus will be on security, but we're going to try and pull in all these other factors that might impact the decision. Okay, and so a general theme of this course that will keep coming up is that there's sort of more to security than security. So it's not, security is impacted by a lot of other things that we don't traditionally consider under the umbrella of security. Okay, so an evaluation framework, we know we're shooting for something that looks like this. So in a little more detail, we're going to have rows and we're going to have columns, okay? And then we're going to have the cells themselves. So the rows are going to be different options that you have to use, okay? So like the VPN, for example, is that the only, you have to think about why you're using it, but is there some alternative to a VPN, right? Like, well, one alternative is no VPN, right? But then there might be other kinds of things that would give you a similar level of security, okay? And so that's what you would put in the rows. Normally what we like is we like the rows to actually be alternatives. So for example, I wouldn't do an evaluation framework that has, I don't know, an antivirus and an intrusion detection and a firewall, software-based client-side firewall, because you could do all three. Okay, they're not really alternatives, and they're sort of trying to address different types of things, okay? So with an evaluation framework, we try to pick things that are actually alternatives, like you would do one or not the other. Sometimes they're not, like sometimes you could think about layering them. So it's not, we're not gonna be super strict about it, but generally it's not like, you're not throwing a bunch of things together in your evaluation framework that are doing they're trying to do different things for you, okay? They're all solutions to the same problem, and you're gonna choose to do one of them. The other thing that we don't put in evaluation frameworks generally is, like, if there's something that is strictly better than something else, then we won't put both of them in the evaluation framework, okay? So it's meant to highlight where there's actually like different approaches to doing things. So for example, let's say we're talking about wireless network security. I could have a chart with like WEP and WPA1 and WPA2 and all the protocols. Well, like there's no reason you would ever use WEP if you could use WPA2, right? Like there's just no reason, right? So that we don't tend to put in evaluation frameworks either, okay? So we take the latest version of everything and that's what we put in. And so apples to apples is sort of saying the same thing maybe as the first point, which is each of the rows are a solution to a particular problem, okay? And sometimes you also have to break the solution apart in order to evaluate it. Like, so for example, let's say I want to evaluate Symantec, like, I don't know, their client-side thing. Well, it's a whole bunch of things. There's malware and there's anti-ads and cookie tracking and whatever. Anti-malware, I should say. But anyways, there's a bunch of different things in it, right? And so I would pull out that thing that I'm interested in. I wouldn't try to evaluate the whole thing. So sometimes you distill the solution down to the actual primitive. And the other thing we're trying to do is we're not trying to compare brand names of technologies to each other, okay? So going with the car example, we're not specifically comparing a Tesla Model C to a Toyota Prius, and we're going to tell you, well, the key fob on the Toyota looks different than the key fob on this. Those are differences, and they are differences that mean things, but the evaluation framework's at a sort of higher level where we're trying to compare the fundamental technologies. Like, fundamentally, is there a difference between a Tesla and a Prius, right? So you might say, well, one's fully electric, the other's a hybrid, right? And you could have a fully gas car like the Golf. And so those are fundamentally different things. So in an evaluation framework, we wouldn't say Tesla, Volkswagen, Toyota. We would say like gas car, example, Golf. Electric car, example, Tesla, Okay, so the brands are sort of examples of what we're comparing, but what we're comparing is the underlying approach. So if there's differences in the underlying approach, that's what we're trying to compare. Okay, questions about the rows? Okay, so in your assignment, you're going to build an evaluation framework. Okay, I'm going to give you the rows. Okay, so the rows you don't have to worry about; they'll just be given to you. So I'll go through the assignment at the end, but just as sort of foreshadowing. The columns is what you're going to have to come up with, and then the actual evaluations themselves. Okay, columns. It seems kind of easy when you see one that's done. You're just like, oh, that's obvious. But actually coming up with the columns and making sure they're different columns and they cover everything, it's harder than it seems. And it's okay to do it sort of iteratively. So sometimes you come up with a column, you put in the evaluation of all the systems, you come up with another column, and then the dots are like exactly the same, and you sit there and think, oh, are these two columns actually measuring the same thing? Because all the systems are coming out the same way. They either have it or they don't have it. And so sometimes you have to play a bit with it. Or you see one that's exactly opposite. Like every time this system gets a check mark, on this other column it doesn't, and then it's a flip, then you're like, well, maybe these columns are measuring kind of the flip of each other. So I don't need two columns. I just need one that measures it. So anyways, there's some iteration that's involved. Okay, another thing that goes towards readability is the columns, we're always going to phrase them positively. So I didn't talk about the cells themselves, but just to foreshadow it, we're going to the model where it's just like kind of a check mark or not a check mark. Okay. Now, let's say the check mark is something like vulnerable to heart bleed, which is the name of some attack. Okay. Is that a column where you want to get that check mark or you don't want to get that check mark? If I say I have a system and I'll get the check mark if it's vulnerable to heart bleed. I don't want it, right? Okay, so I don't want that check mark. It's cost efficient. Do I want that check mark? I do, okay? Now, the problem is that when I look at the chart and I see, oh, this system got a bunch of check marks, well, some of them are good check marks and some of them are bad, okay? So that's really hard to read because I can't get a sense. I have to go column by column and try and figure out, okay? So the idea here is to make every check mark good, okay? How do you make it good? It's just you play with the English. You just flip it around. So instead of saying vulnerable to heart bleed, I would say not vulnerable to heart bleed, okay? So I just flip it, and now it's like I want that check mark, okay? So all your columns should be what you want. And more or less, the more check marks you get, kind of the better the system is, okay? So this helps read, make the chart easier to read. Okay, and then what we'll do is we'll try to sort of shoehorn your evaluation into 3 criteria. Now, for the assignment, you don't even have to do it with the middle thing. You could just do a dot or no dot, but you can, sometimes you feel like there's a system that kind of gets halfway there, and so you can define a partial dot. But basically, what we're going to have is a bunch of rows that are systems. We'll have a bunch of columns, and the columns will be security properties that you want, or other things like cost, deployability, usability, that kind of thing. And yeah, you either get the dot or you don't for that particular column, okay? And so if you fully satisfy that property, we give you the dot. If it doesn't satisfy it, we don't. And if it's somewhere in between, we might define a kind of half dot for you to get. Okay, now whether you're using evaluation framework in your research, if you're using it in the assignment, if you use one in your project, the most important thing you have to do is you have to go first off column by column and say, what does that column mean, okay? It doesn't have to be long, it could be a sentence or two, but you have to have a crisp definition of, okay, what's this column? And then you have to say, what does it mean exactly to get a full dot on this column? What does it mean to get a half dot? What does it mean to not get a dot at all? Because what it means to satisfy is going to change based on the column. Like say I have a column that says inexpensive, right? Well, what does that mean, right? Does that mean like it's less than $5,000? So that's what I would write here. I would say, well, look, if it's more than $5,000, you don't get the dot. If it's between 1,000 and 5,000, you get a half dot. And if it's less than 1,000, you get the dot or whatever, okay? And again, other people may have different numbers, okay? So there's no right or wrong, definition of what's inexpensive. The main point is that you're actually saying what inexpensive means. You're specifying it. So the person that's reading the chart, they know what you're talking about, okay? So you just have to be open and transparent about why things are being evaluated with a dot or not a dot. And you want to be sensible and logical in terms of how you choose it, but everyone in the room might choose a slightly different definition for what it means to get the dot or not get the dot, depending on the property itself. The other thing that you have to do is every time you give a dot, like so for every cell, you need a sentence saying why. Okay, so like for VPN and inexpensive, I gave it a half dot, why? Okay, I gave it a half dot because it costs between $1,000 and $5,000 because you have to do whatever. Okay, so anyway, so an evaluation framework, it is a lot of work. It's a little tedious to write it up, but basically every column should be defined. What it means to get a full, partial, no dot for every column needs to be defined. You don't define it once for the whole table. You have to do it column by column. And then every time you give a dot to a system, or basically for every cell, like every row and column combination, you need a sentence or two saying why you decided that was a part dot instead of a full dot or instead of a no dot. Does that make sense? Okay. So anyway, so the idea is you have to document every little thing. Okay. So in the assignment, you'll come up with a bunch of columns, and then for one of the rows that I give you, you'll do the evaluation and you'll come up with the cells, and you're going to have to say why you decided to give it a full dot, a half dot, or no dot. Okay. So this is sort of the theory, anyways, of evaluation frameworks. Is there any questions so far about it? Okay, so it's pretty simple. Like once you look at the end product, it just looks more or less like this. But yeah, it's a little tricky coming up with the rows and the columns and the cells. Okay, so what I want to do now is we're going to do an example in class. Okay, and the example that we'll do is passwords. Okay, so passwords are something we all use. We've all used alternatives to passwords. Okay, and so we're going to evaluate different alternatives of passwords. We'll come up with the rows, we'll come up with the columns, we'll come up with the evaluation. It's baked into the slides already. I used to do it live, so like based on what you say, we might end up with a slightly different framework. But because it's slides now, like there is a path that I took through this evaluation, but it's more open. It's not like you might disagree with my columns, or you might use different columns or slightly different definitions, and that's fine and that's okay. So on the assignment, everyone's assignment should look a little different because you all will have different feelings about what these columns and things should be. Okay, so there's no exact thing. That said, like if you look at two different evaluation frameworks, they shouldn't be wildly different, right? They should be more or less telling the same story, even though some of the smaller details might be a little different. Okay, so before we go into passwords, I'm just going to give a bit of background on how passwords work. It should hopefully be review. And then we're going to have to use a bit of this when we think about some of the properties that we might want. So this is just sort of, you can put evaluation frameworks out of your mind for a second. We'll talk about passwords, and then we'll look at both of them together.
We have to explain all the background about the problem.
Sort of, so it depends. So it depends on your audience, I guess. So yeah, so in the assignment, because I will give you the background and I'll actually give you the rows. You don't have to repeat that back to me. If you have a client and you think, oh, I'm going to give them an evaluation framework, then you probably would want the background. Yeah, so it depends on the audience, I would say. Yeah. Okay, password. How do passwords work? Okay, so I go to a website for the very first time. I don't have a user account, so there's no record of me at all on that website. And I say I want to set a password and a username. And so I just send the username and the password to the server. This goes over a secure channel. So I have some sort of encrypted channel. So if anyone's in the middle, they can't read my password out of this particular channel. Okay, we'll talk about that channel next class, starting next class. But for now, we'll just assume that it exists. The server does see my password. Okay, so they see it in clear text. They know exactly what my password is. Okay, what the server is going to do is we're going to iterate through. So I'm going to show you a bad server, an okay server, a better server, and I'll show you different options. So right now we're in the world of a bad server. Okay, a server from the 1980s or 1990s. But anyways, this is what a server could do. It's not the most secure option. So they'll have a database, and they'll just have everyone's username and everyone's password. Okay, it's that simple. So if I'm a new user, it accepts me as a new user, then it just adds me to the database, and so now I'm sitting in the database somewhere. All right? All right. Now later what I'm going to do is I'm going to come along and I'm going to log in again. And so when I log in again, I'm again going to send my username. I'm going to send my password. It's going to go across the wire. And it's going to go into its database, and it's going to look up my username based on what I am asserting. And then it's going to check whether the password I'm sending matches the password it has in its database. If they match, then it assumes it's correct. If they don't match, it assumes it's not correct. And it doesn't let me log in. Okay? So that's pretty simple. Okay? So it's a two-step process: registration, logging in. Both cases, I send my password in a way that the server can see it, so it sees it in clear text. And here it's comparing the clear text version of what I sent when I'm asserting as my password with what it's stored as my password itself. Okay? All right, so let's say we want to attack the system. So I want to log in as you. Maybe it's a personalized attack, so I'm targeting you specifically. I don't know your password, but I know that you frequently send your password into this website, and so maybe there's a chance that I could learn your password. Or maybe it's an impersonal attack where, this is a website and I really want to be able to log into this website. I don't care whose user account I get. I got to get someone. Okay, whoever happens to be around on the network logging in at that particular time is fine. Don't really care. Okay, I previewed this next slide, and I know there's a little movie clip, and I always forget to try and make the sound work, but actually don't know if this works. Okay, I'll just show it without the sound. Okay, so let's think about how are you going to get this password out? Okay, as an attacker. And so the way I see it is there's different places that you could sit. Okay, you could sit between the user and their computer. Okay, you could sit inside their computer somewhere. So the password, the user's typing it key by key into their keyboard, right? And then it's somehow going from the keyboard through their computer system, whatever that means, and then eventually it comes out on the network connection in terms of a string. Okay, but there's a lot of people that sort of see it, a lot of processes in the computer that are going to kind of see it. You could attack it once it's on the wire, okay, or you could attack it once it's sitting on the server. Okay, so these are all your different places to attack. This isn't meant to be comprehensive. There might be other ways of attacking it, but we'll just go through these ones and see at least 3 or 4 different attacks that you could do. Okay, so if I'm going to sit between the user and their computer, okay, what does that mean? Well, it means that I'm like watching them type their password in, okay? So for example, I do have to type letter by letter my password, and if you're standing behind my shoulder, you could maybe see what my password is, or get some of the characters of my password, okay? If there's a video camera somewhere, maybe there's surveillance, right? And so I type my password in, and the video surveillance happens to be pointed at my laptop keyboard, you could maybe pull it out, okay? You can do very fancy things. When I press the letter A on my computer and I press the letter P, it makes a slightly different noise, okay? You hear a clicking sound, right? But a computer with a very sensitive microphone could maybe tell the difference between an A being pressed and a P being pressed, okay? And so it could, very sensitive, or the amount of power that's being drawn, right? When I press it, it creates a little resistance, or there's it's all digitized now, so maybe this isn't such a thing, but there might be a way to read the voltage off if there's the adversary sitting on the power line and they can tell what keys I'm pressing. I don't know. Okay. So in general, we call this shoulder surfing. We're going to focus more on the idea of like someone like looking physically at it. Okay. So how should you type your passwords in if you're scared about shoulder surfing? Okay, so you could do that. So some of them will give you like a keyboard, but if someone's over your shoulder, they can also watch you click. They can see what you're clicking on the mouse. They can see your screen as well. Okay, so what you should do, you can barely see it, the resolution isn't good, is you should get a big blanket and put it over your head and over your computer, and you should type your password in under a blanket, okay? And so there's this movie, there's this whistleblower named Edward Snowden, and he leaked a bunch of documents about the intelligence agency in the US, and they made a documentary about it. And so he had all these sensitive files, and he was in a hotel room, and he was scared that there could be covert surveillance and things like that. And so when the journalists were sitting with him, they were actually filming it. That's exactly what he did. And they thought it was really weird. They'd never seen anybody do that. But from his perspective, this was like nation state adversaries that he was worried about. And so he wasn't taking any chances. And so he pulled the blanket over his head. You can see a video. So this is actually, there's a movie, a fictionalized movie about it. And so this actually blends the documentary and the movie. So in some cases, it's actually Edward Snowden, and sometimes it's Joseph Gordon-Levitt who plays him in the movie version of it. But anyways, I'll play it one more time just so you can see. But that's the actual documentary. And then this is the movie version. Okay, so shoulder surfing is something that maybe there's a way around it, right? Maybe not all ways of authenticating are vulnerable to it. So it's something we can think about. Okay, we can think about the adversary being in the computer somewhere. Okay, so a very trivial attack, one that happened here at Concordia, is someone went into the library and they got like a little dongle, right? Something that like plugs into your computer and then you plug a wire into it. And all it did is they took the keyboard. The keyboards were plugged into computers, and the computers were saying, "There's students, you guys can use them. If you're looking up things, you can log in, check your email, and that type of thing." So there was a little dongle, so they just plugged the keyboard into the dongle into the computer. They walked away, left. And what it was doing is it was recording every keystroke, okay? Because the keyboard has to send the keystroke to the computer. It's going across the wire, so it was just logging it. Some of these have like a little Wi-Fi thing, so it can email it or post it on an anonymous somewhere on the internet, so the person can look at the logs remotely. Or you can come back a month later, grab it, put it in your pocket, and then go home and analyze it. So I'm not sure in this case. I think it was a simple one. But anyway, so like someone was in there and they were using the computer and they noticed it and they said, "Oh, that's weird." And so then they, I guess, asked the librarians or the IT staff, and then it turned into a big thing. Like there was this big investigation and things like that, okay? Now, in this case, could you pull a password out of it? So you could, because the person's going to type it in, but you do have to parse it out. So you are getting like you don't know, oh, they're on a website, or like you don't have any of the context of what's on the screen or what they're doing. All you have is literally the keys that they press, right? But if you see an @ symbol, that's probably, an email address or something like that. And if you see a .com, at blah, 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 .com, the next thing that follows it, that's probably going to be a password, right? So that would be a simple heuristic to like pull out candidates for passwords, and then you could try them and see if they actually work. Okay, malware, you can get malware on your machine. It could be anywhere on the stack. It could be in the operating system, rootkit. It could be at the app level. It could be the website itself. You're on a malicious website somehow. You think you're on the real website. You're putting your password into a malicious website. So anyway, there's lots of opportunities for the adversary to sit there. The password is going to get passed, from the keyboard to the driver. The driver is going to package it up, give it to the operating system. The operating system is going to pass it up to the browser because that's where the person's typing in. And so anywhere along the lines, if there's malware sitting there, it has a chance of grabbing the password out of memory. You could sit on the channel between the user and the server. In this case, we're just going to sort of exclude those attacks. We'll circle back and consider them over the course of the next couple lectures. Okay, we're going to spend a lot of time talking about this protocol, which is called HTTPS. It's what's used, like when you go to a website and there's that little lock that appears, that's that protocol. And there's a whole security model behind it that we'll study in lots and lots of detail. But anyway, so for the sake of this lecture, we're just going to assume that it works fine and we're not going to attack it there. And then you could attack the server, okay? So the server has a list of passwords, right? And because this is a 1990s version of internet security, the passwords are actually just sitting there in clear text, okay? So what happens if I break into the server and steal that file? Then I get everybody's username and password for the entire website, okay? You've probably heard about this. You've heard about password breaches, right? That's what this is, okay? So every time you read the news and there's some article about, this website, there's a password breach, or your password might have been compromised because it was included in this breach, that's what they're talking about, okay? So someone broke into the server, they got it. How do you know that it happened, right? How do you learn that it happened? So you might not. There might be like people who have broken into servers, they get that password file and they don't tell anyone about it and they just use it for their own purposes and nobody in the world knows, okay? But usually the reason that we come to know about it is one of two things. Either sometimes the server figures it out. So they go through their logs and they see the network traffic of the person breaking in and then they realize eventually that, oh, this is what happened. And the other thing is that the people that break in, they're specialized in hacking, for lack of a better term. Okay, that's their specialty. Their specialty isn't like, what do you do with these accounts? How do you monetize them? How do you send ads to them and turn that into money and put money in my pocket, okay? Their goal is just like, I know a lot about like vulnerabilities in servers and I can break into any server and steal any file on any server. That's their specialty, okay? So what they're going to do is they're going to sell it to someone whose specialty is, here's a list of username and passwords, let's turn that into money somehow. Okay, and so there's a dark market where these types of things get passed around, and then that's also how you often learn about these things, is that you see the actual file being passed around or shopped, or someone buys it, like a good guy buys it, a good person, and then says, oh, this website was breached. Okay, usually they'll have like samplers, so they'll be like, oh, here's 100 passwords and usernames. You can go try them just to convince yourself that it's real. I have another 1,000,000, and I'll sell you the other 1,000,000. And so, but based on those 10, you can figure out what website it's for and things like that, and then the server will know that it's breached. Okay, can we do anything about storing the passwords in plain text? Okay, so that's one thing that we could do, is we could try and throw some cryptography at the problem. Then we can maybe make this a little bit better. So one idea might be, oh, we could encrypt it. Like if they were encrypted, then that's fine. The problem is if it's encrypted and the user comes along and tells you what their password is, then you have to compare it to something that's encrypted. Okay, so you would have to more or less decrypt this, and then you could do the comparison. But if you decrypt it, then you have to have the key. You can't decrypt it if you don't have the key. So where's the key? Well, the key would have to be sitting on the server somewhere as well, okay? So now it's just I break in, I steal the database, and I steal the key, right? And so it's not actually any fundamentally different to do it, okay? Another idea is that you could, when the person's password comes in, you could encrypt it. You have the database and it's encrypted, and then you could compare the encryptions of the two to each other. Okay, and so this is actually a pretty sensible idea, but you don't even need encryption. In this case, because there's no decryption, you just need a kind of like one-way encryption. So like you take a string or a word or a message or whatever, a password, you do something to kind of scramble it up. If the same password comes in a second time, you follow the same process to scramble it up, it results in the same scrambled up thing. Okay, you'll take a crypto course at some point if you haven't already, and you'll learn that this is called a hash function. So it's sort of like a password where you can't decrypt. It's just like a one-way kind of encryption. Okay, and so the idea, and it's deterministic. So if you always start with the same input, you get the same output. Okay, so those are the two features of a hash function. So what they'll do is they'll hash all the things in the password. Then when the user comes along, notice that they're different, right? This is the hash of the password, and this is the password in raw. But what the server will do is it will simply apply the hash function to whatever the user is telling it, and then it will compare the output of that to what it's stored in the database. If they match, then it assumes that it's correct. Okay. Now, if the adversary is sitting here as the user is putting their password into the website, right? It's coming in not hashed, then they could get the password. Okay. But if they grab this password file when the user's not online or not trying to log in at that particular moment, then they'll just get the hash of the password. Okay. They won't get the password itself. And so then, because it's one way, looking at the hash, you can't figure out what it is that goes in. Then the idea is that it protects it from that type of attack. Okay? Is there any remaining attack that you could do? Say it louder. Sorry. The
physical environment between the user and computer will then, if you secure the destination between the computer and server, even the physical environment between user and computer will remain.
Yeah. So you mean like sitting here, right? Yeah. So those attacks still apply 100%. Yeah. And let's say I break into the server and I get this file, but it's hashed. Yeah? Okay. So tell me what those are great words, but what do they mean? They're the right words.
Matching it with like previously 100 hash passwords.
Okay. So the main thing here is that it goes to this deterministic function. So people think, a hash is a one way, you can't reverse it. That's true. But like I said, if you start with the same thing, it will always end up at the same thing. Okay? So you can still guess, right? So I don't know what the password is that produces this hash, but I think it's dog. I can hash dog, and if it comes out to that exact string, then I figured it out. I didn't do it by reversing it. I did it by guessing the input and finding the output. Okay? So you can still do guessing attacks on these even though they're hashed. Okay? So what people do is they will take a hash function that's used a lot, like SHA-3, okay? And what they'll do is they'll take the top million passwords, the top 10 million passwords. They'll build dictionaries from it. So they'll take all the passwords that have been released in database breaches back when when it was like raw passwords. Okay, they'll take all those passwords, they'll put it through SHA-3, and there'll just be a file that sits there, and it's indexed by the output, and it just has like what's the input that produces that output. Okay, and so you're looking at a particular output. You look into the file, into the rainbow table. It might be there or it might not be, but if it is there, then you know what the input is. Okay, and they did a lot of work because hashing millions and millions of passwords is hard work, and they do all sorts of tricks. Like they'll take a common password and add 1, 2, 3 to it, or they'll replace every letter E with the number 3 because it kind of looks the same, and people make you choose one letter and one has to be capital and one, whatever. Or they'll take a normal password and they'll just put an exclamation mark on it because that's a special character, okay? So all those tricks will be in the rainbow table, and so as an attacker, you just download the table and a bunch of the passwords are going to match, okay? If I care about attacking you specifically, this may or may not help. It depends on how good your password is. If you have a good password, it's not in any rainbow table, then you're fine, okay? There's no problem with it. But if I just want to get anybody's account, like I really want to get into this website, I don't care whose account it is, I just need one, then as long as one user uses a weak password that's in a rainbow table, then I'm in. Okay? So anyways, yeah. Okay, what can we do? So there's one other trick that we can do. The first thing we can do is basically we can't stop the rainbow attack. Okay, we can't stop it. We can only do one thing, which is basically try and slow it down. Okay, so one thing we could do is instead of hashing the password once, we could hash it 1,000 times. Okay, it takes a little longer. The computer has to do it a bit longer. So when the server pulls your password in, now it has to apply the hash function 1,000 times, right? and then check it against what it stored, where it also applied the hash function 1,000 times when you registered. So it takes a little longer. It takes milliseconds instead of microseconds. But the server's not really going to feel that difference, and you as the user aren't going to feel that difference. It's still happening really fast. Okay, who's going to feel that difference? The person building the rainbow table, right? Because now it's 1,000 times slower for every guess. And the idea of a rainbow table is you're going to put millions or millions of guesses, okay? So it's now going to take you 1,000 times longer to build that exact same rainbow table, okay? So that's one trick. The other trick you can do is you can add a kind of key to it, okay? Now the key isn't going to be a secret, okay? The one reason the rainbow table works is because we're assuming everybody uses SHA-3, okay? So I build the rainbow table for SHA-3. The website you're attacking uses SHA-3, therefore you can use my rainbow table, okay? But what if every website used a different hash function, okay? Then you would have to build a custom rainbow table for every website, okay? What if every user of every website, their record was stored with a custom hash function, okay? So Alice, when the website stores Alice's password, it uses one hash function. When it stores David, it uses another hash function. Every user account uses a different hash function, and every website uses a different hash function. So like your password record on this website is like literally the only thing on the entire internet that uses that exact hash function. Then someone has to build a rainbow table for you. Okay, you can't reuse it across. Okay, do we have millions and millions of hash functions that we can pull one randomly and use it to you? We don't. But what we can do that's cryptographically equivalent is when we hash something, we can just throw in a random number, okay? So if I throw in the random number 5 with your password, right, it's like a different hash function than if I threw in the number 6, okay? So we call this a salt, okay? So it's a unique random number. It's just thrown into the hash as you hash it. And the important thing here is it's not a secret. It's not a key. So when the adversary breaks in, they know what the salt is, okay? But if they don't have a rainbow table for that salt, then they don't have a rainbow table, okay? And so if you're using a different salt for every single user, and every website's using a different salt, and they're big enough, then you can't build all the rainbow tables for all the salts. There's too many salt values, okay? And so that also kills off this rainbow table. Again, you can still guess. The adversary can still try the passwords, but they have to start from scratch, and they're only breaking your password. Okay, so you've turned an attack that kind of works on, let's just get any user's password off of any website into more of an attack where I'm going to try and crack this user's password. Okay, so anyway, this is the sort of the state of the art. So today, if you're deploying a web server and you're going to store some passwords, you're going to do something. There's actual functions like KDF2 and things like that. But the essence of them is that there's some salt being added, and there's some iteration to slow the hash function down. Okay, questions about that?
You store the salt in the same server.
Do we start the salt at the same?
Store, yeah. Because if it's not the salt, not solid.
Yeah. So the salt would. I should improve these slides, but like it can literally be sitting right beside the password itself. So say Alice salt 55, and then here's the output of the hash.
Yeah, because if I store the hash, it's not the salt.
Yeah.
But at least I have more tools to work.
Yeah. So your idea is to not store the salt with the password, or
in anywhere else.
Yeah. So you can do anywhere else. The problem is that the server, because Alice is showing up with her real password, at that point they have to try and figure out whether it's right. And they can't do that now until they have the salt. And so the salt, they're going to have access to the salt like at their fingertip.
Yes. It's going to be strong, but more secure.
It's more secure, but it slows the system down because they have to fetch the salt. And then the salt also will at least temporarily be in memory as well. But anyways, we can discard that attack. But yeah. Yeah, so you could have the salt sitting somewhere else. Then you could actually use encryption and just call it a key, and then you decrypt it one by one. But yeah. Okay. Okay, we'll just jump into this. All right, so let's go back to evaluation frameworks. Okay, so those are just some of the details. You can see different ways of attacking passwords, and we'll think about those when we come up with things. Okay, so the idea of passwords goes back, I don't know, to the 70s or the 80s. Basically, there was a time when like a computer would be used by one person. One user, one computer. Okay, one computer, one user. Then eventually people decided, oh, maybe multiple people will share a computer because they were expensive. Maybe a university has a computer and different people are sharing it. And so initially, if I logged into the computer, I could see all of your stuff, you could see all of my stuff. Okay? And so then eventually they're like, well, we need to separate accounts. And what is it that, like, how does the computer know it's me and not you? Let's use a password. Okay? So that was the idea of a password originally. And then when the web came out and we had this idea of personalized web, like in the early days of the web, it was just websites, everyone saw the same website. There was no concept of like, this is your inbox and this is my inbox, kind of. But when the web became personalized and we had accounts and things like that, they said, well, we have this password model for computers, let's just do it on the website itself, okay? Now, the ideal of a password is, I don't know about you, I use a password manager. I have at least 1,000 websites in my password manager, okay? And so the idea would be that I would choose 1,000 different passwords, right? They would all be good passwords. They'd be like random and all of that type of stuff. I wouldn't write them down anywhere. They would be in my head. And if I go to that website that I haven't been to for 3 years, I would somehow be able to recall from my memory what that unique, random, long password was, for that website and log in. Okay? So that was the mental model of how passwords should work. Is that a good model? From a usability perspective, it's a terrible model. Okay, so in reality, we don't like that model. Okay, is there something we could do instead of passwords? So is there any way that I could log into a website that's not just strictly a password that would be better in some sense? Okay, all right. We'll do it. You don't put your hand up, just shout it out, but I'll pause you. Okay, so the first thing I heard is someone said biometrics or face. So yeah, we'll call that biometrics. So that could be a fingerprint, it could be an iris scan, it could be some sort of facial recognition. So this MacBook has a fingerprint scanner. My phone has the face camera. Your devices may have different types of things. They're basically biometrics, okay? What's the advantage of the biometric in one sentence? Why is it better than a password? So it's unique, correct? Portability, okay, so it's always going with you. Do you have to remember anything? Do I have to remember 1,000 passwords? I don't, right? But what if someone steals my finger? Then they can log into 1,000 websites, right? What if I lose my finger? Okay, anyways, think about these things. Okay, biometrics, what else? At least I have 10 fingers, right? So it's like I have 10 chances. Just shout it out. Okay, so someone said client certificates. So there's this idea that you might have a cryptographic key on your computer, okay? And now it's not something I remember, it's something that is stored on my computer. And so when I go to the website, it just automatically sends it. So there is an earlier version of the web that was based on this principle. So you would never have a username password. You would have what's called a client certificate, which would have this key, and you would do this kind of crypto thing with the server, and it would figure out who you are based on this certificate that you have. The idea kind of died. I would say like almost no one used it. But now what I've seen is it's reemerging under the name secure keys. So if you use an Apple, for example, you've probably gone to websites that are like, oh, do you want to set up a secure key? And in this case, it's actually it's a wrapper. So it's a biometric plus a client-side certificate. So it's some cryptographic key that's on my computer, but it's protected with some secure hardware. And the way I unlock the secure hardware typically would be with my fingerprint. But there's probably, maybe if I put my password in for my system account or something like that, there might be a way of getting it out. And then usually websites, like say I lose my computer, then I've lost my key. Okay, that's the problem with client certificates. But yeah, often there's, like a lot of these technologies, there's a different way. You can be like, oh, I lost my computer, and then you can reset it or something like that, right? So a lot of different ways of logging in to, like there's some backup that's like a different way of logging in. And so you're really evaluating like 3 or 4 ways of logging in instead of 1. And the adversary, by the way, will choose the easiest, right? So they might have a hard time logging in as you, but they could go to the website and say, I want to reset the password, right? And then they might have an easier path to getting access to your account than actually nabbing your password. Okay, so client certs, biometrics. Just shout out. Okay, so some sort of physical thing. Okay, so the physical things that I remember are, there are things that you plug in. Maybe it has like a fingerprint or something like that. So in that case, it's more just like capturing a biometric or things like that. One thing that's very common are there's these things called RSA tokens. Now you tend to use your phone more, and so it kind of met up with another technology that we might as well talk about now that we're talking about it, which is two-factor authentication, right? So they're basically the same idea, which is you have a username, you have a password, but now you have a code, and you have to type that code in as well. And the main difference is how do you get that code? And how does the server know that it's the right code, okay? So in two-factor, the server will send the code to you, and it might send it to an app that you have installed on your phone, or it might send it to you in a text message or an email. Okay, so that's two-factor authentication. The RSA is like a little, looks like actually kind of like this. It's just like a keychain thing. It has a screen on it, and it has that code. And the code just changes every 30 seconds, or you press a button to change it. There's different ways of doing it. And so you put in your username, you put in your password, and then it says, what's your code? Then you take your dongle and you type the code off the dongle, you press enter, and somehow the server figures out that that number is correct or not, okay? How does the server figure it out? We'll talk about that later. I'll tell you a story much later about how every RSA token in the world got broken, but that will come later. Yeah?
I don't think we can have any alternatives for the passwords, because in the first step, if you want create your account, then you use for example an alternative, for example 2FA and biometric.
Mm-hmm.
You used to set a password with your email account, for example.
Yeah.
To set an account, create an account, and then use for example the alternative.
Right.
In the first step, you are using password.
Yeah. Agreed fully. So the point is that are these actually alternatives for one of two reasons? One is, do they kind of go through the password scheme first before they pivot into two-factor or anything like that? So for the sake of the evaluation framework, we're going to assume that somehow you're able to go directly to a biometric, or you're able to go directly. It's fiction, I know, but if that's the world, like if we decide, hey, if you could go directly to a biometric, and that's the most secure, most usable, cheapest, it meets all the criteria, gets all the dots, then the world will change, okay? So the fact that the world hasn't changed maybe is telling you something, okay? That's a message in and of itself. But anyways, we're going to make that assumption. And the other thing that we're going to set aside is we're going to set aside the idea of resetting. So resetting is also another mechanism that basically comes down to, can you access your email? I've never seen a reset mechanism. Like the fanciest authentication schemes, if you have access to my email, you can always reset it. You can say, I lost my phone, I lost my computer, and then it's like, fine, we'll just email you a code and a link, you click on it, you can reset your password, yeah? And so I think that's kind of like the base layer of everything. But anyways, we're going to ignore that, and we're going to evaluate them as if it's just that primitive itself for the sake of comparison. Okay, what are, so biometrics, two-factor, hardware tokens, OAuth. Okay, so the idea here is, okay, so I download a new game on my phone. I want to play it. It needs a username password for me. Do I really have to create a new username password, right? What if, I have a Facebook account, I have a Google account, I have a Twitter account. Maybe I could log into Facebook, and then somehow the app would use my Facebook account to authenticate me instead of creating yet another username password for the account, okay? So we call that single sign-on, and then OAuth is sort of the protocol that passes because it has to be a three-way dance in this case. So I'm logging into Facebook, but the website knows that I'm logging into Facebook because it's sending me there. And if Facebook says yes, then it also has to tell the website, yes, I said yes to this user, it is that person. And so there's a sort of three-way protocol between you, the identity provider, and the person that you're authenticating to, the game in this case. And so, yeah. So OAuth would be the main protocol that would be used in that space. Okay, so single sign-on, it's great. Why does Facebook do it though? I mean, now every time I log in, I mean, they have to have a server, and the server's sitting there and it's doing stuff, right? Like that costs electricity, and it's a bunch of bandwidth to Facebook, and like why would they do that? Like, it makes no sense. Okay, that's exactly right? So why are they doing it? Because every time I play the game, Facebook knows. They know what game I'm playing, they know when I'm playing it, and that's useful to them. That's worth money. It's worth the money that offsets the cost of the extra infrastructure of, handling all of these authentication things, okay? So if you aren't paying for the product, you are the product, is the standard saying. Okay, single sign-on, anything else people can think of? Okay, so graphical passwords. So on Android, for example, you used to, I don't know, you had like a scan thing where you would sort of draw a password out. So it's still a password, it's just in a different format. The idea of it is it's somehow more usable. Okay, so that I can remember a pattern better. It's sort of muscle memory, although when you type, you get muscle memory too. Whatever the case is. Actually, there is a lot of research. So this topic has been studied. Is a graphical password easier to remember than like a text kind of string or something that you choose? And if users were asked to choose one, are they going to choose something that's more random than if it's just a piece of text? And so in terms of how they choose, both of them are weak. So like normally, like people will pick a simple pattern, right? Or there are a lot of other studies, like they'll show you a picture and you just click on 10 things in the picture, right? But lots of people are going to like click on the interesting things in the picture, and no one's going to click in the like middle of the blue sky where it's just like in the middle somewhere, right? So you get these sort of hot spots in terms of where people click. So whenever humans like do things and they try to behave randomly, it's really hard to do. And so you get clustering around certain things. I'll show you an example too later of that. But in terms of your ability to remember a password, graphical passwords are much better. And the way our memory works too is there's two types of things. So there's, let's say I'm watching a movie and there's an actress in the movie. I'm like, I know that person. I've seen them before. Who is that person? Okay. So what I've just done is called recognition. So I recognize, I know that person. I've seen them in some movie before. Okay. Then when I think of their name or I think of the movie that they were in before, that's called recall. So I recalled it, okay? So recognition is kind of like a lower bar. Like you might recognize a lot of things. Like I recognize that person, I don't know where they're from, right? And then recall is like sort of the higher step. And so passwords are based on recall, right? You have to recall your password, otherwise you're not getting into the website. But with graphical passwords, you can play with recognition-based systems. So what I could do is show you 10 random pictures. One of them you've seen before. And if I ask you ahead of time, what's the password the picture that you use for your password, you're like, I don't know, I don't remember. But when I show you 10 of them and it's mixed in, you'll be like, oh, it was that one. I recall that, right? I forgot what it is, but now that I see it, I know that's the one that's familiar, okay? So you can build these authentication systems that just use just use recognition rather than recall. They perform really, really well on usability, but almost no one uses them, right? And so why is that? Okay, well, we'll throw them into our evaluation framework and maybe we'll figure it out. But. Say louder.
Active Directory, Microsoft 8.
Okay, I don't know. I've heard the term before. I don't know exactly what that is, but it's
Basically, an identity provider.
Yeah.
Your Windows mostly use it over the network. So it's a centralized place where you can store an identity.
Yeah.
And for authenticating, for any application or not, it
Yeah.
will consult the identity provider, which is the Microsoft in-house. It's just like an SSO, but overall it's on-premises, like in your system it stores and all.
Okay, so I got it. So there's two things that, so I'm an Apple user, so maybe it's equivalent to Keychain, which is the Apple thing, but what you're describing sounds more like single sign-on. But Keychain itself is yet another thing that we didn't talk about. And so maybe it's sort of a merger of the two. So there's the idea that Microsoft would serve as your identity provider. Then it's like a single sign-on kind of system. The other thing Microsoft could do for you, or Apple does for you, is it could just remember your password for you. So you just say, I have this, I go to this website, and it can build it into Safari or Edge or whatever the browser is. And so it just knows, it's like, oh, you're on a website, there's a username and a password box. Hey, I see you're registering, do you want me to I can make a password for you? It's going to be a great password. It's going to be completely random, and I'm going to remember it. You're never going to have to type it in. When you come back to the website, I'll just tell you, hey, do you want to use that password I created for you? You click on it and it's good. And oh, by the way, because you have an Apple TV and an iPhone and a MacBook, I'm going to sync your passwords across it. So when you're sitting on your TV and you want to log into Netflix and you have this big complicated thing, you don't have to, it will just say, do you want to use your password, right? It's not going to make you type it in, look it up in the thing and then type it in. Okay, so those are password managers. So those are also good. In personal disclosure, that's my preferred method. So of all the alternatives that we talked about, I use a password manager. I think it's the best balance of all the things. It's not perfect, nothing's perfect, but for me anyways, it's the best balance. But you don't always have that choice. Sometimes you're forced to use two-factor authentication and things like that.
So why would they save your password?
So why would I?
Yeah, why would they spend?
Oh, why would Apple do it? Yeah. So again, it depends on the configuration. So there is a configuration where it's sort of in the cloud. The pro of this is it's synchronized around, but the con of it might be just the same for single sign-on, which is Apple knows every time I log into a particular website because it's giving the password, and they're monetizing it, and so that's why they do it. That could be reason one. Reason two, though, sometimes your password manager is just on your computer, right? Like it's nowhere else. It's not synchronized. That has its trade-offs when you sit down at a new computer, but it also means that there's no like password sharing and things like that. And then the reason they do is just to sell computers. It's just a feature that they add, and maybe you'll buy that instead of a Windows because you like the feature or whatever. Or users want it, that type of thing. So I don't think there's a strict path to monetization with offering it. Okay, other questions? And Apple makes money off this now, like they've kind of played up their privacy angle. So like a lot of their marketing and things like that are privacy oriented. And so they'll add features like automated like MAC address spoofing and things like that. And they'll give it a fancy name. And when they give keynotes and things like that, they'll hype up those types of things. So it helps with their brand as well to have a password manager. And by the way, if you do have a Mac and you do use their password manager, it also does two-factor authentication. So you have to set it up, but it's not really like, it's not like they don't advertise it, I don't know why. But like when I log into Moodle, right, I could demo it for you, maybe. So this is my user experience. So it remembers my password. Okay, so I just click it once and the password's in. Now it's like, oh, I'm going to do a two-factor thing. Okay, and so it remembers my two-factor. I press it, it spits it in. It should. It doesn't work because Microsoft Online is buggy. But basically that was the user experience, is it would then spit in my two-factor code. So I just tap my finger twice and then I log in. And if this website weren't buggy, it would work, but it is buggy. And so anyways, yeah, that's my plug for Keychain. Okay, so I think we did pretty good. Let me just go through them quickly, then we'll go on break and then we'll come back and actually do the evaluation. So we talked about two-factor. We talked about graphical, we talked about biometrics, we talked about client-side certs or having some keys. By the way, if you do cryptocurrency, that's my main research area, it's all based on keys. Okay, so you have keys, they're stored on your computer, you have some client like MetaMask and it's managing your keys and things like that. Password manager like Keychain. Hardware token, this is what it looks like, the RSA one anyways. And so again, it is basically two-factor. It's a hardware form of two-factor instead of using your phone. Single sign-on, so you can sign on with different people. And then we're not going to talk about resetting your password. That's a different thing. And there's other things that sometimes people shout out, like CAPTCHAs. So CAPTCHAs are involved in that logging in process, but they're not your actual password. They're something slightly different. They're trying to make sure that you're actually a human. You're not an automated service. There's different things around geolocation. So like if I'm logged into Gmail already, that's another whole thing. Like I'm already logged into a website. I come back to it. Do I have to put my password in again, right? And so there's these things called cookies, and the cookies are designed to not make you type your password in every time you go. We'll talk about cookies also in this course at some point, like much later in the course. We'll go through all the details of it. But anyways, everything with cookies and where you're coming from, those are things that we're sort of setting aside, okay? So our goal after the break will be, here's the rows of our table. We're going to need some columns. And what are they going to be? And then also we're going to have to put some dots into the table itself, okay? Then I'll talk about the assignment, and then that's good. All right? So take 10 minutes and come back at 10 after, and then we'll continue. All right. Okay, so now we're going to move on to the evaluation frameworks question. Sorry, to say it loud. If everyone can quiet down, I can't hear the question. Yeah. Okay, zero knowledge proofs is the question. So a zero knowledge proof would factor into a cryptographic key. So they're usually based on a key itself. And the idea is, if we go back to this thing, so here the user sends their plain text password over the channel, and then it's processed by the server and compared to what's in the database. With a zero knowledge proof, you basically wouldn't send the password. So the server would somehow be convinced that you know the password that matches this without me actually sending it. So it closes down one additional attack, which is either the adversary that's on the wire or the adversary that happens to nab the contents of RAM in the server at the exact time that you happen to be logging in. Yeah. Now the problem with it is it sounds awesome, but I could also steal more or less your zero knowledge proof. So if I can replay your proof to the server, then it's going to believe that I know the password even though I don't. Okay. So you have to be careful that the zero knowledge proof doesn't turn into a kind of password itself, where anyone who can spit out these values in this order. Right, and there's ways of doing that involve some interaction, but now it's an interactive protocol and not a non-interactive protocol, and so the point is it gets a little complicated, the details, but it is a better way of doing it. But at the end of the day, in terms of what does the user have to remember, it's still in the cryptographic keys type of thing. Yeah, and when you go and sign something, that's more or less a zero knowledge proof. So a signature is. Hey, I know the signing key for this public key, and by the way, I'm going to attach my proof. I'm going to staple it to a message, and at the end of the day, that is what a signature is at the end of the day. So as long as you're signing something somewhere in the protocol, you're effectively using zero knowledge, even though people might not call it that. But yeah, when you take a crypto course, you'll learn the relationships between these primitives. Okay, other questions, comments? Okay. So the next thing that we need is a set of columns, okay? And so what we're going to do is, this is useful for almost everything you do in security, not specific to passwords. But one of the first academic papers that came up with this idea of an evaluation framework is this paper. They use the example of password alternatives, which is why I'm using it as well. And I'll show you their evaluation framework at the end. Not in detail, and the paper's linked to on the Moodle, so you can go read it. If you want to see what a real evaluation framework looks like, you can read the paper. But anyways, they had this idea that to make sure that you're capturing enough columns, it's useful to sort of split them up into three categories. So the categories they came up with are usability, deployability, and security. Okay, so our UDS framework, okay? So usability is everything to do with the user using the system, Okay. Deployability is everything about what's the infrastructure, how, like what stops me from just using it tomorrow. I decide today I want to use it. Can I have the system up and running in 5 minutes? If the answer is no, why? It costs too much. I have to put up servers. I have to change your computers. I have to enroll a bunch of users. You know, there could be lots of different answers to that question, okay? Those all are going to fit under the deployability sort of cluster. And then security is what we know about. Okay, so we'll go through one by one, and then we'll try and think in terms of passwords specifically, what are some of the criteria that we could use, okay? So usability from the user's perspective, more or less how easy is the system to use. Deployability from the provider of the system, how easy is it to set up, okay? So cost, infrastructure, uptime, that type of thing. And then security, how secure is the system? For the user, it could be for the service provider, it could be for other people that are involved in the system. It could be about privacy. Sometimes privacy is split out. In our case, you can think of Stride. Again, when you come up with these columns, you might use Stride as a way to brainstorm some columns for security. One of Stride is the I, information disclosure, which is the privacy component. So we'll consider privacy the same as security or a subset of security. But sometimes people like to split privacy from security. Okay, so here's some examples of usability properties that you would want from a password or an alternative to a password, okay? All of these are framed positively, meaning you want these properties. They're not framed in such a way that you don't want the property. And so we could imagine having a dot or no dot with whether you meet each of these, but we're going to have to do the additional work of saying what exactly does it mean to get a dot or not a dot. Okay, so we'll come back to that later. But okay, so like one of the big problems with passwords is I have to memorize a bunch of stuff. Okay, so if there's nothing to memorize, I'm just using my fingerprint, that's great. Okay, I can learn how to use the system. Okay, I know what passwords are, I've used them forever. It's sort of an easy mental model. Cryptographic keys, and I have to store it. If I sit on another computer, it's not there. That's like a new mental model. Maybe that's hard to learn. Easy to use. Again, this is kind of vague, but like you would drill down and say, what exactly does that mean? Easy to use. Nothing new to carry. So do I have to carry around an RSA token now? And I have to take it everywhere I go, right? That's something new to carry, right? Whereas if I do single sign-on, I don't have anything new to carry. So single sign-on in that regard anyways is better than RSA tokens, at least for that one property. Is it the kind of thing that scales up to 1,000 passwords, right? So the idea that I would memorize a unique password for every website, that does not scale to 1,000, okay? If I have a password manager and it's remembering them all, and I just have to remember one master password that unlocks the password manager, that doesn't matter if I store 10 passwords or if I store 1,000 or 10,000, it's all the same to me, okay? So that's an idea of something that would scale. How many errors do I make, right? I have this code, it's on my phone, and now I have to type it, or I'm looking at my RSA token, and there's a 8-digit code, and I have to type it into my computer. And then I'm halfway typing it in, and then it changes, right? So these are things where I might make errors or they're frustrating from users. We can think about, is there something to lose? I lose my RSA token, right? I lose my finger, right? Whatever the case may be, right? If you introduce these things, then you might introduce new things that could be lost. And if losing them, kind of breaks the whole system, then that's a problem. Deployability, you can think of things like how expensive is it? How much does it cost? Do I have to put up new infrastructure? Do I have to put up new servers? Do I have to change everyone's computer? So assume, like, for example, you're logging into websites, so maybe it's about changing your browser or something. But like everyone has to install this extension because I have this like crazy authentication scheme. That's not a good system from a deployability perspective under that category. One that they use in the paper is how mature it is. So it's like some new idea that somebody had last month as opposed to something people have been using for 10 years in the military. It just hasn't filtered out to common use. The second thing would be considered a mature technology, whereas the first thing when, again, you would, this one's like more sort of subjective, but anyways. And then they also look at how open the protocol is. Is it something where like only Apple knows how it works? or it's like OAuth and like everyone can look at it and figure out how it works. Security, this is a small set of things that we could look at, but this sort of plays on some of the security threats that we saw at different stages of you entering your password, okay? So I could just try and guess your password, okay? If you're using a password, you chose the password, I could maybe guess it. I have a good shot at guessing it. If you're using your fingerprint, I'm not probably going to be able to guess that. Maybe I will. Then we have to ask the question, well, how easy is it to guess someone's fingerprint, right? We'll circle back to that. What about just impersonating you? I know a lot about you. I know a lot of the details of your life. I know the name of your kids and your pets and your birth dates and all that stuff. Does that help me in any way? It could, right? If it's a password, maybe your password's based on it. We didn't talk about it, but there's some weird things like social authentication, or Facebook had this thing for a while where it was a reset mechanism, but it would show you pictures of your friends and it would show you a bunch of pictures of not friends, and you had to say which were your friends and which weren't. And then it would let you reset your password if you did that right. The problem with it is when they pulled random pictures from your friends and not friends, they didn't pay attention to privacy settings. So if someone had put a picture on Facebook that was private, this authentication scheme might pull that picture in and show it to someone else that's logging in. So they got into trouble for that. Resilient to external observation. So you have malware, you have a keystroke logger, something like that on the computer, right? Does a keystroke logger, obviously if I'm typing a password in, that's a problem. If I use my fingerprint, it's maybe not a problem, okay? Because it's not, it depends, maybe it goes down to like how you define what it means to log keystrokes, but anyways. Shoulder surfing is a better example, right? You can watch me type my password in, that's bad, right? You could actually guess my password if you watch me type it in enough. Okay, but if I sit here scanning my fingerprint all day, right? I'll let you watch me all day, tap my finger, and it's not going to help you log in as me. Okay. That said, you could pick up my phone or my glass or something like that, and my glasses or something like that, and get my fingerprint probably. Then you could 3D print your like rubber finger, and you could make it with a conductive material, and then you could use it to log in as me. Or I could have a backup. In case I lose my finger, I'll just have a 3D printed backup just in case. Or if I want you to log into my account because I'm away on vacation, I'll give you my 3D fingered print and you can log in for me, and then I'll take it back from you when I get back. Phishing is another thing. So I go to a website and it's Google with 3 O's. It asks for my password. I don't notice it. So I go and I type my password in. Now the attacker has my password. Okay. But if I'm using a password manager, my password manager will say, oh, actually, you don't have a password saved for Google with 3 O's. And I'll be like, okay, something's weird here. I thought I had a Google account, but I don't know my password because it's this big, long, random thing and it's storing it for me anyway. So I'm not going to accidentally just type it in, right? So then I have to investigate or try to open it up and try and find it. And I have a chance anyways of catching the fact that it's a phishing attack. Resilience to theft. So like, is there something I can steal? I steal your phone. You're using 2-factor. Does that help me in any way? I steal your RSA token. Trusted parties. So like I'm using Facebook to sign in to the game. Now they're a trusted party that's basically sitting in the middle. Okay, so I'm not going to go through all of these. What I just sort of picked a random three from each or something like that. And we'll just to give you a flavor of what it looks like. And then you can see the paper I'll show you at the end if you want to see like a full thing, okay? So the next thing we have to do is we have kind of like our columns. So now we have to say, what does it mean to get a full dot, a half dot, or no dot for a particular column, okay? So let's say that our usability requirement is easy to use. What does that mean? Like it's easy to, like cognitive easily, like what, like, so you have to drill down a bit, and I might settle in on, okay, I'm talking about like kind of a physical thing. Physically, it's easy to use, okay? So like every time I type my password in, I do some physical effort, okay? So if I never have to type anything in, I just scan my fingerprint, right? Or it recognizes my face. That's basically as close to effortless as you can get. So that's good. I'll give those kinds of systems a full dot. Okay, I have a cryptographic key. I just go to the website and I'm logged in, right? It did the whole transaction. I didn't press a button, right? That's great. No physical effort, right? I have a password manager. It has a master password. I have to type it in once, but now it's unlocked, and now I can log into 1,000 websites, right? Well, I put some physical effort in because I had to do at least one password, but I don't have to type in 1,000 passwords, it just auto-populates it. Maybe I give that a half dot, okay? You might be different. You might think, oh, that's so close to a full dot, we'll just give it a full dot. That's fine, okay? It's subjective. Not everyone's evaluation frameworks are gonna look the same. I'm choosing that I'm gonna give that a half dot. And then if I log into 1,000 websites and I have to type in 1,000 passwords or do 1,000 swipe patterns or whatever, type in 1,000, random codes sent to my phone 1,000 times for 1,000 websites, then that's doing really, really bad on this effort thing, and I'm not going to give it a dot at all. Okay. What do I have to memorize? So again, I'm going to use this like 0, 1, 1,000 kind of paradigm. So if I don't have to memorize anything, it's my fingerprints already on my body. That's a full dot. I have to memorize my one master password or my single sign-on. I have to know my Facebook password, but then because I'm using single sign-on, I can log into all my other websites. Then that's a half dot. And if I have to memorize 1,000 passwords for 1,000 websites, then I'll consider that no dot. Do I have to carry things around with me? So I have this new RSA token. I got to carry it with me everywhere I go. I'm going to consider that no dot. Okay. I don't have to carry anything. It's my fingerprint. I'm carrying it anyways, right? So that would be a full dot. Then you can get into a middle. And so again, you don't have to have a half dot for everything. Okay. Half dots are sort of optional. So if you feel like a half dot doesn't make sense, that's no problem. But here I might say, well, what about two-factor authentication? So I got to carry my phone. If I go on a run and I need to log in or something, and I don't know, I'm logging in somehow from my computer, I don't have my phone, I don't know what the scenario is here, but I do have to carry my phone. So it kind of is, but I'm carrying my phone anyways, and if I'm in the place where I'm logging in, I'm probably logging into my phone, or I'm logging into with my computer. If I can carry my computer, I can carry my computer on my phone. You might say, who cares? That's sort of, you're carrying something, but it's not a new thing. It's sort of what you're carrying around anyways. So we'll give that a half dot. Okay. All right, we can think about guessing attacks. Okay, so I have an idea of what your password might be. Or sorry, I don't have an idea. I don't know what your password is, but I know 1 million common passwords. I can try all of those. Okay, so there's two ways of doing a guessing attack that we distinguish. One is an online and one is an offline. I have some slides, so I'll go through them. Basically here I'm just going to use either you are resistant or you're not, and then we'll consider both of them in turn. So an online guessing is like when, like say I grab your debit card, I don't know your PIN. Okay? What I have to do is I have to go to the ATM and I have to go 0, 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, and after 10 times it's going to lock me out, okay? Or I don't know your Facebook password, so I'm going to go to facebook.com, I'll put your username in, I'll guess dog, and then I'll guess fish, and then I'll guess cat, and then again, I'm going to get locked out eventually, okay? Or they're going to slow me down, or there's different things that the web server can do, okay? So we call this online because you're going through the front end of the server. The server sees all of these failed attempts. The server has a chance to do something about it. So it might slow you down, it might lock you out. There's different types of things, okay? And so because you're benefiting from two security mechanisms, one is that your password's unique, so the person doesn't know it exactly, and the second is that the website is doing some protection for you. Because you have both of those things, your passwords don't have to be as good. They don't have to be as unguessable because there's a chance that the website will step in before they actually guess your real password, okay? The alternative would be, let's say I steal the hash database of a server and I can throw a cluster at computers or I can rent a botnet to do it or whatever, and I can guess as fast as I can with as many computers as I can. All I have to do is guess it, hash it, doesn't match. Guess, hash, doesn't match. Guess, hash, doesn't match, okay? In this case, my password needs to be more unguessable. Okay, it needs to be longer before that adversary reaches my password. Otherwise, I'm going to get cracked. Okay, so if you want to put numbers on these things, you can think that like you need about the equivalent in terms of coin flips would be like flipping 64 coins. That gives you a certain pool of randomness called entropy. So that would be like kind of you're resilient to the online thing. And then if you want to be resilient to offline, you want to flip like 100 or 112 or 128 coins in order to get that much equivalent randomness in your password. Or you can think of it, maybe an easier way is, how many different combinations are there? Well, if there's 2 to the 64, that's a lot of combinations, but a computer could exhaust 2 to the 64, and we couldn't assume that the system would necessarily prevent that. So I can get locked out, but then I can wait a couple days and then come back and things like that. Whereas in a back-end guess, I can, Bitcoin's network does 2 to the 80 hashes every 10 minutes or something like that. So, you need something like a lot more combinations. Okay. Generally, if something is human chosen, this is the basic heuristic. We say it's not secure against either online or offline attacks. Okay, so I wouldn't, even if you get locked out and things like that, I don't think that's enough of a security mechanism to say some human chosen secret is good. Okay, so the only things on our list that I would give like the dot to would be things where either it's not fully human chosen, or it's a combination like two-factor where you have a password and you have a randomly chosen number that the server gives you that you have to type in, okay? But you need some sort of randomly chosen stuff, okay? Now, the basis for me saying that is based on a picture that I want to show you. So this comes from a paper. The paper is linked to on the website, on the Moodle. And it has this picture in it, and I love this picture, and I know you're looking at not knowing what this picture is, but I promise you in 5 minutes you're all going to love this picture too, okay? This picture is like my favorite picture in all of computer science. I'll tell you the story behind the picture first. So there was a website. It was like this social networking thing before the days of Facebook. It had a kind of music orientation, so it was called Rock You. And someone broke in, they stole all the passwords, and this was the days before they had this common sense to hash the passwords or salt them, okay? So they literally had all the passwords just in clear text, okay? And there were like hundreds of thousands of users, okay? The other thing that was significant about the website is they had absolutely no rules about what password you could choose. If you want your password to be the small letter A, that could be your password. Okay, so there was no it has to be 8 characters, it has to be numbers and characters and capital letters and all that stuff. Okay, so what a lot of people did, this is sort of earlier days of the internet, is a lot of people chose a 4-digit PIN. Okay, they had it anyways, they probably had it for their banking or whatever. And so if you went through the leaked database, you found, I forget what the numbers are, but there's like hundreds of thousands, let's call it, of just 4-digit PINs that people were using as passwords. Okay, so then what you could do is you could pull out that data set, and it's small enough that you can actually put every 4-digit PIN on a slide. Okay, it's a small enough space that you could actually, and that's what this picture actually is showing you. Okay, showing you every single combination of a 4-digit PIN. The way you read it is the first 2 digits of the PIN are along the x-axis, and the last 2 digits are along the y-axis. And so if you want to look at the pin 1, 2, 3, 4, you would go to 1, 2 on the x-axis. You go to 3, 4 on the y-axis, and there's a little square. You can see it's kind of gritty. There's little squares. That's the pin 1, 2, 3, 4. You can see it's sort of a dark blue here. Okay. Now the last thing is, well, what's the colors represent? So 1, 2, 3, 4 actually happens to be kind of a darker blue than everything that's around it. So what this is mapping is how common that password is. Lots of people pick it, it's going to be dark blue. Not a lot of people pick it, it's going to be light blue. Okay? Now, let's say a computer's picking 4-digit pins. Okay, it's picking them randomly. You get mailed a 4-digit pin, and you use that pin, you don't reset it. What should this picture look like in terms of which is 1, 2, 3, 4 a more popular or less popular pin than 5, 7, 8? If it's randomly chosen. Okay, the picture should be just one shade of blue. Okay, all passwords are equally likely. It's completely random. There's no structure or anything like that. Okay, is this picture one shade of blue? Okay, so what do you see? Patterns. Okay, so what are some patterns that you see?
Same number repeated.
Okay.
First one, second.
Okay, let's go with lines. Someone said lines. So I see a couple lines. There's kind of a line here. There's a line here. There's a line here. What? Just pick one. Okay.
First two and second two
Okay.
are same.
All right, let's do the diagonal. Okay? So the diagonal line, what does this represent? Well, it means that the first two digits of the pin and the last two digits are the same. Okay? So if I went 1, 2, 1, 2, it would be somewhere on the line. Okay? Now, if you look closely, you can see that some are actually even darker. So like this one it's on the line and it's particularly dark. Well, that's actually where all four digits are the same. 4, 4, 4, 4. Okay? If you go up to 5, 5, 5, 5, you get a dark one. But the line is there for that complete pattern, but those ones are particularly emphasized. Okay, what's this line here? There's this horizontal line. Okay, dates more specifically. Okay, so years. Okay, so this horizontal line is actually, it's hard to see, but it's actually at 19. Okay, so it starts here at 19, this would be 1960, 1965, 1975, it goes all the way up, then it jumps over one to the 2000s, and then it sort of dies out around 2010 kind of thing, and that's when that breach happened. Okay, so this breach happened a while ago. Why, it's obvious, but for the sake of completing the idea, why is that a common password? Year of birth or something like that, okay? So if people are less than 100 years old, it's going to be somewhere in this sort of dark region, right? Okay, what about this like kind of, I call it the castle looking thing here. It kind of looks like the side of a castle, like a moat. So let's think about it. So if you look really closely at 0, 0, it actually, that shape isn't there. It only kicks in at 0, 1. So at 0, 1, the castle goes up to 31. Then it stops. Then at 0, 2, it goes to 30. Then it goes to 31. Sorry, I should say at 0, 2, it goes to 28, but sometimes 29, right? At 0, 3, it goes to 31. Then it goes back to 30, and then 31, then 30, then 31 twice, then 30. Any ideas? Okay, so the first is the month. Like think of a birthday, right? My birthday is January 20th, so 0, 1, 2, 0. Okay? Would you have 0, 1, 32? No. Okay? And so that's exactly where it stops getting dark, right? And so you can actually, if you know nothing about human civilization other than the passwords that they choose, you could look at this and figure out, well, they have a year-based system. It's sort of like 4 digits. It's now around year 2000 and something. And, you know, in the Georgian calendar, they have 31 days and then 28 days and then 30 days. And you could read the whole calendar out. Okay? Now, I should note that when Canadians do like dates, I forget actually how it is. It always confuses me. I think we go day, month, but Americans do month, day. Okay? So no problem. That's here too. So you can see that there's this like castle shape. And then if you go down here, you see that it's flipped on its side. And you see that that exact same castle shape is here. The screen is kind of stained right there or something. There's something weird going on. But anyways, you can see it's kind of less popular. This one's a little darker, but it's definitely there. Okay? Then there's all sorts of other things you can read off of it. So month, month, day, 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 month, month. Years, so 19XX, 2000XX. There's mathy kinds of things. So like 1, 2, 3, 4 was popular. 2, 4, 6, 8 is popular. 9, 8, 7, 6 is popular, at least relative to its neighbors. It's not like really, really dark blue. Anything along this diagonal, including like repeated digits, 4, 4, 4, 7, 7, 7. Probably the most darkest square on this is 69, 69. No idea why. There's also a horizontal line at 69 here. It's a music website, so there's some like references to pop culture. So Van Halen had an album called 5150. Usher had an album called 8701. So those are pretty popular. This one's kind of weird, but on cell phones, you didn't used to have keyboards. You used to just have like the digits. And so if you wanted to text someone, you would have to press the digits, and the digits would map to letters, and you would press it a certain number of times to get different, because there's more letters than digits. But anyways, if you wanted to text someone the word love, you would press the number 5, 6, 8, 3, maybe a couple times each. But That became slang, sort of internet slang for love. So anyways, and there's lots of other little dark marks that we didn't talk about. And so you could literally like go through all of them and you could find lots of different things that are interesting about this chart. Okay, so the moral of the story is, now let's say you're an adversary and I know you have a 4-digit PIN, I want to guess your PIN. Am I going to guess 0000, 001, 002, 003, 004? Probably not, right? I'm going to guess 1, 2, 3, 4, 6, 9, 6, 9, 1983. I have like a priority list. There's passwords that are a lot more common, and then there's some weird passwords that almost no one picks, okay? And so I'm going to go through the passwords from the most common to the least common, and that's what every password cracking tool does. Okay, Johnny the Ripper or whatever you want to use, it comes with a dictionary of passwords. It's not going A, B, 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 C, 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 right? It's going from the most common to the least common, and so it's likely to crack weak passwords a lot faster than strong passwords. Okay, another thing is resilient to external observation. So if I'm standing over your shoulder, so like a fingerprint, a password manager, a client key, those all happen automatically. I'm not typing something into my keyboard. If I'm typing something in my keyboard, there's a chance that a video camera or you watching me could figure out what my password is. There's theft, physical in this case, not digital. So I steal something like your phone or your RSA token or something like that. In deployability, we can think about how much it costs. So the way I split it was like, if it's free, it gets the dot. If it's not free, and you have to pay for every user. So you have 1,000 users, you pay 1,000 times a certain amount. If you have 2,000 users, you're paying twice as much now. Then I give you no dot. And then sometimes there's like, you have to go buy a server, but once you have your server, it doesn't matter. You can have 10 users or 10,000 users. You've already paid the amount. So I'll give you a half dot if it's sort of a fixed one-time cost, but if it's a cost for every user, then it's no dot. Okay, and then here's the actual evaluation framework. So again, this is kind of a toy example of it. It's a little simpler than what you would do on your assignment. It's a lot simpler than anything you would see in an academic paper, but for the sake of us just doing one in class, it does the purpose. So you have your rows, you have your columns. We have a definition of what every dot means in every column, which I'll just sort of remind you of here. And then now the only thing left to do is to actually go through the systems and think about whether they get a full dot or a half dot. And if you do a really good job, in your rows are actually all like fundamental technologies and they're not overlapping, they're not like combinations. Your columns are all unique columns. You have a really good definition of exactly what a full dot means and a half dot means and a no dot. The actual going through dot by dot and assigning it should be super easy at this point, okay? So if you do a lot of work on really refining your columns, it should be just very, very clear, right? So like, do you never need to type, draw, copy anything to log in, okay? Well, the only ones would be like something like your cryptographic key that's on your computer. It does it automatically for you, or a biometric. Okay, every other one you're doing something at least once. Okay, some of them you're just doing it once. So a password manager you might have to unlock first. So that's one password. And a single sign-on you'd have to log into Facebook, let's say with your password. But then after that you can log into everything else. And then everything else, graphical passwords, you're typing them in for every site. And then these ones are even worse, right? Because not only are you typing a password in, you're copying some code or something like that that you have to type in as well. So you might like do the half dot differently. Like you might say these things are really bad because you're typing something in addition to the password. So maybe they're the ones that should get the half dot. And if you just have to type in a password and nothing else, then maybe that's the half dot. So there's different ways. And again, you can go to like quarter dots, 3/4 dots, half dots, but all of this affects the readability, right? So this table here is pretty simple, right? I can kind of look at it and get a feel like keys look pretty good, RSA tokens look pretty bad, passwords look pretty bad. You know, you can kind of get a feel from it because it's simple, right? So the simpler your criteria and things like that, the more readable it is. So you have to find that right balance, but anyways. Do I have to memorize things? So you can see, this is where it's interesting, so I did this on purpose. You can see that U1 and U2 actually are exactly the same in terms of their evaluation. Okay? So if you're doing your evaluation framework and you see this kind of thing, it's actually a good reason to stop and pause and ask yourself, are U1 and U2 actually the same thing? Because if at the end of the day, maybe I'm double counting some property, like they're phrased differently, they seem to be about different things, but maybe at the end of the day, they are about the same thing, right? Maybe, right? So U1 is like, how many things do I have to type in? And U2 is like, how many things do I have to memorize? So those sound like different things, but maybe everything that I memorize, I ultimately have to type in, right? Right? And then you can think about, well, is there some system which you wouldn't have to memorize, but you have to do a lot of typing, but no memorization, right? Or conversely, is there a system where you have to memorize a bunch of things, but you don't have to type as often, right? And if you can come up with one of those sort of counter systems, first off, it might give you another row for your table. And then secondly, you can say, okay, these are different things, okay? But you might also decide, these are basically the same thing, so we should collapse them, okay? So anyway, so this is the kind of thing. The other pattern you might see is the flip pattern, where everything that gets a full dot gets an empty dot. Basically, it's the exact opposite all the way down, and the half dots are the same. So that's another indication that they're not independent columns, they're maybe dependent or measuring sort of the same thing. Nothing to carry. So if you're carrying an RSA token, you're not going to get the dot. If you're carrying around your phone, it's something you're carrying anyway, so we give you a half dot. And then everything else, there's nothing new to carry. Whether it's online or offline. So basically, the way I said is if a human chooses it, I'm not giving you a dot on either. If it's a machine-generated random number, I'll give you the dot on both. Okay? It doesn't have to be the password. It could be the second factor, but at least one factor is some machine-generated random number. There's lots of entropy in that, so that's okay. And then the middle category is sort of where it gets vague. How random is your fingerprint? Is a fingerprint more random than a password that you choose? Is it more random than a password that's randomly assigned to you from a computer? And so the literature seems to indicate it's sort of in between. So it's more random than something that you would just choose yourself, but it's not as random as if I just had my password manager generate me a random password. There's a lot more entropy there. Okay? So you could maybe exhaust every fingerprint possible if you had a computer or a bunch of cluster of computers to do it. You could try every fingerprint, and eventually you would hit the right one. But if you were going through the front end of the system and it was like slowing you down and locking you out and things like that, then you probably would never guess the person's fingerprint. Okay? And again, that's sort of an art, not a science. Like, you can find these numbers somewhere in the literature, but your iris is different than your fingerprint. And there's also a tolerance, like, I can take a more accurate read of my fingerprint, so there's more randomness, but then it's more likely to change. If I put my finger slightly wrong, or it's wet, or I don't know, I was swimming and my finger expanded or something, it's more likely to think that it's not my fingerprint, even though it is. Okay, so all of these biometrics also have a kind of error that you can tweak between accuracy, like false positives and false negatives. You can tweak between them. Anyways, shoulder surfing. Can I look over your shoulder? So if it's a biometric or a key, biometric, you can watch me tap my finger, it doesn't help you. Keys, my computer just does it, right? And it's done. There's nothing to see. Things like password managers and single sign-on, if you shoulder surf me typing in the master password or my Facebook password, then you can shoulder surf. But if that's already done, then there's nothing to shoulder surf, okay? So then I gave that a half dot. I called it vulnerable on first use. And then things like, where you're typing your password in every time with or without a second factor, those are things that are not going to get anything. They're vulnerable to shoulder surfing. Now, you could argue that two-factor, well, if you shoulder surf me, you get my password, you maybe get my second factor that time that you shoulder surf me, but later when you go in to log in as me, you only have my password and you don't have my second factor, right? So that's where maybe that's more like a half dot than an empty dot, right? And so the way that you define the half dots might vary a bit. Okay, so I'm not saying like this is science and everyone in the room is going to come up with this exact configuration. Physical theft, I can seal your finger. It's kind of gruesome, but it's more like lifting your fingerprint as opposed to like cutting your finger off. I can seal your computer, which has your key on it. So that's actually a pretty serious threat. And then most of the other ones, it's some sort of thing that's in your head or something like that. And then in terms of deployability, so the biometrics and RSA tokens is the easiest to understand. All the users need an RSA token. It's not free, right? And I have to give it to you, so there's going to be some cost, and it's a per user cost. Biometrics, it's not that your fingerprint's free. I mean, you already have it, but the reader isn't. Okay, so the reader isn't necessarily on every device. If you can assume it's on every device, then it's free. Like maybe it's the Face ID, and most devices have cameras. But if I need a special reader, then it's not. So you're going to make some assumptions as well when you evaluate these things, which is typical as well. But under the assumption that you need a reader, then I'm going to say it's not free. And every user needs a reader. And then something like single sign-on, I got to throw a server up. The server is going to help run OAuth. And so that's a cost, but it's more or less a one-time cost. Okay. Obviously, the more users, the more busy it will be. But anyways, in terms of the strict hardware costs, it's a one-time cost. So I'll give that a half dot. Okay. Questions about this general process? Hopefully I made it look easy.
No, compared to the assignment, we want, you said that the roles, you were going to give the roles.
Yep.
to the assignment.
Yep.
So categories should be those ones, stability, security, and
Yeah. So I'll at the end I'll actually open the assignment up and we'll go through it together. But you'll see there's specific language about that. So yeah. Okay. Which is the best? Just shout out what you think. Okay, does anyone think keys are the best? Okay, and why? But like, why is it? It's an obvious question, a dumb question, but just answer it for the sake of answering it. It has more dots, okay? All right, now the moral of an evaluation framework is you shouldn't actually do that, okay? It's not meant for you to literally count the dots, okay? Because there's things that keys don't get, like security against physical theft. Maybe I care a lot about it, right? Maybe that's like the number one thing. Like all my users are leaving stuff lying around all the time. And like physical theft to me is like the number one thing, okay? We're going across borders all the time and the police can seize anything. And like, you know, if it's in my head, it's fine. But if it can be seized, that's a big problem for me. It's maybe not a big problem for you logging into Facebook, but for me and my application, that's a big problem. You can't tell me that keys is the best solution, okay? And so dots aren't equal weight. So some people will consider some columns, I'll say columns aren't equally weighted, okay? So it's not like every column is as important as every other column, okay? And which columns are important depend also on the context and to the user. Different users will have different preferences. They'll care about different things, okay? So some people will like to put a total at the end and say, oh, keys, that's like 1, 2, 3, 4, 5, 6, 7, right? And passwords is a 3. Okay, don't do that, okay? Your job with an evaluation framework isn't to tell the message. Your job is just to illustrate what the trade-offs are, okay? The reader is the one that's going to interpret it, and they're going to decide what the columns mean and which ones they care about, okay? So that's not the end goal of an evaluation framework. It's really to present all the options in a fair, neutral way, and then let the user decide, or the reader of the evaluation framework. Okay. Now, if you open up the academic paper that I base this on, you'll see that it's much more complete. Okay, so what we did in class is a toy. What they did is publish at the very top security venue, like period, IEEE Symposium on Security and Privacy, otherwise known as Oakland. And so in terms of your assignment, maybe if you do, you don't have to do this in a project, but some people choose to do it. Are you doing this or are you doing this? Well, you're going to do something in between, okay? This would be great. I mean, if you did this kind of thing, that would be awesome, but I don't expect something as detailed as this. This is probably too much of a toy, though, for even your assignment itself, okay? So try and shoot somewhere in between. A lot of the detail is number of columns, number of rows, but it's also the detail that goes into describing what a dot means, what a column means, and all of that type of stuff. So if you go through the paper, you'll see they have about a paragraph for every column and exactly what it means and what a half dot means and a full dot. So there's a ton of detail. And there's not a dot in this chart that you, like, they give P plus tan, whatever that is, a full dot on resilient to targeted impersonation. Somewhere in the paper, there will be a sentence that says why that's a full dot. Okay? There isn't a dot that's in this chart somewhere that's not described somewhere. Okay? So that's what makes an evaluation framework complete. But anyways, you can see we do a pretty good job. So like Password Manager, they look at a couple different configurations that basically boils down to whether there's a master password or not. They have some proxy-based stuff we didn't talk about. For single sign-on, we sort of treat it as one category. They look at like 6 different ones. Graphical, they go into a couple different specific schemes. There's this whole like cognitive password thing that we didn't talk about that no one uses. It's just academics write papers about it. I won't even describe it. It's kind of weird. There's some like paper-based things. So you like kind of have a grid, and then you go on the website, and then you sort of spell the website out on your grid, and then it spits out your password for you. And yeah, so they're kind of weird. Again, like people don't really use them in real life, but academics write papers about them. Visual crypto is its own thing. Hardware tokens, so we talked about RSA, but there's other different types of things. Two-factor, they look at a bunch of different subtypes of two-factor authentication. Biometrics, they look at fingerprint, iris, voice. We kind of bundled it together, although you can see that they evaluate almost the same. Voice does a little bit better on some of these deployability properties, probably because microphones are more common in devices than an iris scanner or a fingerprint reader. That's just my guess. I don't remember reading that. And they also look at recovery a little bit in the end. And then in terms of their columns, I know it's really small, you can't see it, but they have 8 usability, 6 deployability, and 10, 11 security properties, something like that. So it's a lot more detailed than we went to. They're usually a little more specific. We were kind of like, oh, it's easy to use, right? But they'll say something like a much more specific, like it's, well, actually they do say efficient to use. So it is actually kind of simple language, but their attacks are like very like fancy sounding, like resilient to internal observation or resilient to leaks from other verifiers. And so like you almost have to go and read what that definition means to understand exactly what it is. But anyways, so this is what a complete evaluation framework looks like. Oh yeah, and then their sort of takeaway. Yeah, question first.
What's there's also like it can be boxes on the columns where in the cells.
Yeah, the colors.
Yeah, the colors.
Yeah, so the colors is something that. Okay, I'll tell you what it means, and then I know some of the authors on this. I'll tell you their feeling about it after. But basically, they said the incumbent system is passwords. And so another thing that we wanted for our chart is we want you to be able to compare how good it is relative to normal passwords. Yeah? And so if it did worse than normal passwords, it got a red square. If it did better than normal passwords, it got a green square. And if it was the same as passwords, it got a white square. So if you see a lot of green, it doesn't just mean it's good across, it means it's good specifically relative to passwords. So it's the kind of thing that you want to flip to. Now, their feeling about it was they noticed that when they did deployability, because passwords are everywhere, they're basically perfect on deployability. You can see they get a solid dot on every deployability perspective, right? So everything is going to be at least not as good as, at best you can be as good as passwords, you're never going to be better, and you're probably going to be worse on some of these properties. And so in this middle kind of column, everything's red. There's no green anywhere. And so they felt that was kind of a misleading message, but they didn't know how to fix it. And anyways, eventually this was the final version that was published. But yeah, that's what the colors mean. Yeah. Okay, so there's two kinds of, so the question is what kind of information, you look at this chart, so what kind of thing. So there's two things you can do. The first is the second thing. It could just be a resource. It's there. I want to know how is two-factor compared to passwords, and then I can look up the two rows and compare them and decide I really care about these columns and make some decision about it. The other thing that you would typically do in a paper is you would take some interesting results. So it's more subjective, but I might look at this and, for example, one of the interesting results is basically when they look at it, they say nothing is clearly better than passwords, right? There's things that are, for everything that's a little better than passwords in some regard, it's worse in some other regard, okay? And so a question for everyone in this room is, let's go back to this. How many people have used all of these things? Okay, all of them. Okay, how many people have used all of them except for maybe two? Okay, probably lots of you. Some people are shy, but like maybe you've never used keys or an RSA token, but you probably used everything else, right? At least once, right? So why is that? Why do we have 6 different authentication types? Like why can't everyone agrees that passwords are bad, that's fine. So why doesn't everyone just say, okay, password managers, that's good, done, right? Why is Concordia using two-factor and not single sign-on, right? And why, and so their takeaway, when you do a chart like this, their takeaway is, well, there's no clear winner, right? Everything's sort of good for some people, but not for other people, or there's some aspects that are good and some aspects are bad. And so when it's sort of a mess, and there's a bunch of trade-offs and there's no clear winner, you're going to end up in a world where 10 different people do 10 different things. Yeah? So those are the kinds of observations that you could make. Now, your chart may turn out differently, and you might say, oh, actually, this one thing is strictly better than everything else. And I think in time, eventually, everyone will switch to it, right? And so you can sort of project what you think. And anyway, these are the kinds of observations you can make. Yeah.
Let's consider two situations. The first one is, for example, a company wants to the password, and the security is in the highest level.
Yeah.
And the second situation is in the lowest level. How we can get information from this figure to choose this kind of these two conditions?
Okay. So that applies to any trade-off that exists, but yeah, you might have like a high security system, but say a classic example is like low usability, high security, or high usability and low security, right? It's not a strict trade-off, but that tends to show up a lot. So how do you decide? The answer is the chart doesn't make the decision for you. All it does is it presents to you like sort of a finer grain of what that trade-off is, and it tries to let you decide in the end. Yeah. Okay. All right.
Empty spaces mean not application?
Yeah. So they also had the way they did the dots were different. So we did full, half, no dot, or empty. What did we do? Oh yeah. Okay. Yeah, so in this chart, you can read it here, but it's kind of small. Nothing, an empty space is the equivalent of no dot, meaning it doesn't fulfill the property. Dark dot means that it fulfills the property, and the ring is their half dot, so it's half dark kind of thing. Yeah, so that's just the metric that they use, and the exact symbols that you use don't matter either. So these are things. Also, you'll find that when you use Unicode, like the half circle is like bigger than the full circle, and like there's all these like weird Unicode things that you'll have fun like trying to like depict this, but you can do other things. You could do colors like traffic light, like red, green, blue, or red, yellow, green, or whatever you want. Like you don't have to use dots, but anyways. Okay, and anyways, so their quote basically in short is just that I go through the chart, there's nothing that's a clear winner. I compare it to normal passwords, there's nothing that's even like they're better, everything's better in some regards, but worse in other regards. Therefore, our conclusion at the end is probably we're not going to see in 5 years everybody's using exactly two-factor or everyone's using single sign-on. It's probably going to be this situation where everyone's doing different things. And this paper was written, 2012, okay? And so it's got even more crazy in terms of two-factor, you barely see that in 2012. maybe if you worked at a company or something like that, but like now it's everywhere, right? And password managers are on every computer. Back then you had to install LastPass or something else to even get a password manager. Now it's like baked into the operating system. And so like this sort of fragmentation of different authentication types has just increased over time. And this chart sort of tells you why that's the case. Okay, let's jump to the assignment then. Now I have to do the two-factor thing myself. And of course, there's no cell service in this room because we're deep in the bowels of Concordia. I guess I'll just do it this way. Okay, and it crashed on my phone. This is all the adventures. This is actually a really good, a good lesson for everyone. So, by the way, if you ever want to see what Keychain looks like on Apple and you're not an Apple user, so I have a password manager. I unlock it. I find Concordia. Oops. And then I try really, really hard not to hover my mouse over the password and display it on YouTube forever. But this code is fine. It's only good for 30 seconds, and you need my password anyway. Okay. Okay. So your assignment is individual, so everyone will do it by themselves, no groups. You can do groups on the project, but for every assignment, it should be individual. You can chat with your friends about it, but you shouldn't write the exact same thing or copy like any text from another person's assignment or from assignments that were submitted in past years. Although this assignment we've only used once before. Okay, so you can sort of read the thing. I won't actually just dictate it to you. But the idea is I wanted something that's kind of like passwords where there's different ways of doing things, but not exactly passwords. And so what I settled on that's sort of interesting is, we have these music concerts, obviously you go, and one of the problems with, first off, the authentication that's involved in a concert is a ticket. So you can go to the concert if you have the ticket. If you don't have the ticket, you're not going to the concert, okay? And one thing that bands want, and I've gone to like Canada Music where you can like some of these places, industry events, and heard, record labels and, venues and bands themselves like talk about this kind of stuff. But, when they offer their tickets for sale, they want the fans to buy them. Okay, that's their ultimate goal. But what ends up happening is scalpers will buy up all the tickets in 30 seconds, right? And then they'll try and resell it to the fans, but at a higher price. Okay, and in particular, a band might be like, we're rich, we don't care if we'll sell our tickets for $20, right? Like it doesn't matter. But if a band literally sells their tickets for $20, scalpers are going to buy them all for $20, and then they're going to sell them for $200 or $2,000. Right? And so at the end of the day, fans are paying $200 or $2,000 anyway, right? So like bands literally cannot like lower the price of tickets and actually have it like be consequential, right? So then there's all sorts of things like they have fan clubs, and if you're in the fan club, you get this code, but then the scalpers join the fan clubs, and so it's this whole like kind of cat and mouse thing, okay? So anyway, so there's no like right or wrong way to do tickets, but that's like kind of one problem that people want solved. Another thing that you could do to combat scalpers is make it a lot harder to transfer your tickets, right? So if it's a physical ticket, I can buy it, I can give it to you, and then you're in. There's like whoever is holding the ticket at the end of the day, they're going into the concert, right? But it could be some sort of digital system where the ticket's assigned to you, and then when you show up, it's maybe you show ID and you show your ticket or something like that, okay? So you could imagine there could be alternative things for that, okay? Now, you do want people to be able to resell their tickets, okay? If I buy tickets and I can't go because we get sick or something like that, it's my right to resell it, okay? So you can't just turn off reselling and say, well, we don't like scalpers, so we're going to turn it off, okay? Another thing happens is you might buy tickets online. You get them, there's some sort of digital ticket, you have the QR code, you go to the venue, they scan it and say, oh, you're already in the concert. What do you do? Right? You just paid $200, $2,000, I don't know, for this ticket, and they're like, well, you're already in the concert, right? So someone sold you a copy of a ticket, it was a legitimate ticket, or they sold the same ticket to 10 different people, and one person got there first, they got in, and everyone else is stuck, right? It's not the venue's fault, it's not the band's fault, right? You don't know who you bought it from, it's just some online account, right? So like, what do you do in that situation, kind of thing, okay? So there is room for like tickets, to try and do tickets in different kinds of ways, right? And there are attacks, like could you sell the same ticket to 10 different people? Well, it might depend on the system itself, right? Like say it's a physical ticket, but there's some sort of security, like you need special paper, then it might be hard to sell the same ticket to 10 people. If it's just a QR code, then it's easy. If there's some sort of database where this ticket belongs to this person, when I buy the ticket, I can look it up in the database and see it's my name there. Then I'm happy, then I know that it's real and it's legitimate, okay? So anyway, so there's no right or wrong way of doing tickets, but there are different ways that you could do it. So I just sort of made up, these are kind of theoretical examples, but there's 3 examples of different systems that you might do. So one of them's a kind of physical ticket system, and then you can read the details of it. One of them's a kind of electronic kind of thing, like where you have QR codes. And then the other one's more of a, we'll call it a database system, where you have tickets and they actually are assigned to users and there's something in the database about it, okay? Now these all have different trade-offs. Some of them might help with the scalper problem. Some of them might help with the, like, selling 10 copies of the same ticket problem. Some of them are easy to check, right? The person that's standing there, they just take your ticket and that's it. Some of them are expensive. You need a special reader, or you need an internet connection because you have to look up something in the database and you have to check someone's ID, right? And so that might be worse on deployability. I might like lose my ticket. What happens? Well, if it's a physical ticket, I'm out of luck. If it's some sort of database thing, maybe I can show my ID, prove that the ticket belongs to me even though I lost the ticket. Okay? So as you can see, there's different trade-offs. Okay? I'm not going to give you all of them because that's your job. Okay, so your job is to think of what are actually the trade-offs between these 3 systems in terms of deployability. How expensive is it? Do you need servers? Do you need internet connections? Do you need special devices? All of that kind of stuff. You can think about the security. Does it prevent attackers? Does it prevent scalpers? Does it prevent people from double selling their tickets? Is there privacy concerns? Does the band know everyone that showed up to the concert? Like whatever you can think of. And then you can have usability as well. Okay, usability can be from the ticket holder's perspective. I have something to lose. I have to carry something. I can't lose this. It can be from the perspective of the person that's looking at the ticket, right? Like I just scan it, done. Or I scan it and I get your like user ID, and then I have to look and compare user ID to you, and and then I have to type it all into a computer, and then it checks a database, and if the internet's down, whatever. Like there could be differences in terms of usability. Okay. All right. So the assignment, anyway, it touches on 2 things. So we touch a bit on Stride, and then we touch a bit on evaluation frameworks. So the first thing is to go through each of the 6 Stride categories and come up with, okay, let me read it because it's very specific about what you're going to do. Okay, so what you're going to do is you're going to start with the physical ticket system. So you're going to read how this system works. Another thing I'll emphasize, this is a sparse description. It doesn't necessarily describe every little thing. And sometimes there's more than one way of doing things. You are free to make assumptions. okay? So you're free to fill in the details, and you probably will. And I just want to leave it open-ended so different people can go in different directions. So that's why not everything is like locked down to a science, okay? So there's a lot of like kind of wiggle room in terms of how this system works. As long as it works like this, and as long as the TA can read what your assumptions are, then it's fine, okay? So you can say, well, it doesn't exactly say how this happens, so I assume it happens like this, okay? And that matters somehow for the attacks that I'm trying to prevent, okay? So you'll go through the physical system, and you'll do STRIDE for the physical system. And you'll basically say, yes, there's a spoofing attack, and here's what it is, or no, I don't think there's any spoofing attacks here, okay? And if your answer is yes, there is a spoofing attack, someone might show up with the wrong ticket or a fake ID or something, then you just say that's what the attack is, and this is what the system does to combat it. And what it does to combat it might be nothing. It does nothing, or it assumes that like you can't fake an ID, or whatever the assumption is, okay? So just read the assignment carefully. It tells you exactly, and each of these things you can think of as kind of like a sentence, okay? And then in total you should have 4 or 5 sentences. Then what you do is you compare it to the other two. So you just say, when we move from physical to e-tickets or to online, does anything change? So you might say it's all the same, it doesn't matter, spoofing's the same in all these systems, or you might say, well, it's actually a lot different, okay? Then for the evaluation framework, what you'll do is you'll come up with 6 security criteria. It can be based on what you decided for STRIDE. You'll come up with 6 usability and 6 deployability somewhere. Oh yeah, sorry, 6 usability and 6 deployability. You'll say what every dot means. What does it mean to get a full dot, half dot, no dot? Half dots are optional. And then you don't have to build the whole chart. All you have to do is just evaluate one system. So I chose the online system. So this is the one that you can run. You can do the row for that system. You don't have to do the row for the other 2 systems itself, okay? And you don't have to make a chart. You don't have to have a grid. You can just say like bullet points line by line. Like for usability 1, I gave it a half dot because of this or whatever. So it can be a list as opposed to a chart. Anyways, and then there's some other like papers that use evaluation frameworks that might help you or might not help you. And yeah, anyways, we're over time, so I'll keep it brief. Maybe what I'll do at the start of next class is I'll go through it again and just, by then you'll have read it and you might have some questions about it. But does anyone have a quick question about anything we talked about? Okay, so go read the assignment, try and start on it and start thinking about things. Any questions you have, ask me, send by email, or next class, at the start of class, I'll answer questions. You have 2 weeks to finish it, so you can take this weekend, all of next week as well.